Hello, everybody. Welcome to SVS 317. This is best practices for building interactive applications with AWS Lambda. So if anyone's accidentally wandered into the wrong room, now's your chance to quickly make your exit. My name is Ben Smith. I'm a senior developer advocate for AWS based inside the serverless product team. I'm actually based out of the London office in the UK. I've been with AWS about 2.5 years. This is my third reInvent, second one in person. And since joining AWS, I've done a lot of work on serverless for web developers, stuff like the serverless development workflow, how you move your code from local into production and test in the cloud. I've done a lot of work on serverless and PHP, because before joining AWS, I was a PHP developer for about 15 years. Random fact about me, I used to be a ski instructor and a race coach living in Japan and Canada, and I once got to teach David Hasselhoff how to ski. If anyone doesn't know who he is, then good for you. Really, the most important piece of information on this slide is my contact info. So if there's any questions which I don't manage to cover during the course of this 60 minutes, then please do reach out to me on Twitter or via email. My Twitter name is Benjamin_L_S. So this is the sort of broad agenda of what I'll be talking about in this session. I'll be defining exactly what I mean when I say an interactive AWS Lambda application. We'll talk about business logic, and with serverless, business logic normally refers to Lambda. We'll talk about the difference between synchronous and asynchronous, and how you invoke your Lambda function synchronously or asynchronously, and the impact that has on your application when you might choose one or the other. We'll also look at how you can implement that on a real production-ready web app, and I'll show you some examples of that in motion. And everything I talk about today is really in service to these 4 fundamental goals. I want to help you to increase the value that you are offering to your customers, help you increase the reliability of the applications that you're building on AWS, and of course help you increase the resilience to faults and failures and scalability. Really, every talk that you attend here at reInvent should be in service to at least some of these goals. And of course, to be able to do it as quickly as possible. Okay, so today's focus, Lambda-based applications, and more specifically, interactive Lambda applications. So broadly, what I mean by this is anything that's using a Lambda function where that Lambda function is invoked using an HTTP request and returns back an HTTP response. Now, this can be any number of different types of applications, right? It can be connecting 2 different services or different applications together, and we'll have a look at that use case in more detail in a moment. It could be extending an existing application. It could be an existing SaaS application that you're using, or an on-prem application, a traditional web application, extending it so that some component of it is serverless. It could be to kick off background asynchronous processes with Lambda as well. Of course, web applications is a massive use case for interactive Lambda functions, and that's kind of the underpinning theme of this session, really. And then there's things like data processing, chatbots, Alexa skills. Alexa is actually the first thing I ever did with Lambda was to make an Alexa skill that helps me track my running stats. And I think Alexa is a really nice way of kind of learning how Lambda works. So first, we'll start with this very simple example web app. So this is basically an app that uses a webhook, and it connects GitHub to Slack. And the way it works is that whenever you start a repository in GitHub, it will use GitHub's webhook mechanism to send a payload, a JSON payload, to a Lambda function. That Lambda function will perform some kind of transform, some compute on that inbound payload, and then it will send on to a Slack channel to notify you that you have a new star on your repository. And this actually forms the basis of a whole series of getting started content, which you can go to at s12d.com/getting-started. It's blog posts, example code, and you can build this application from the ground up. So this is the output of that application. This is the kind of message that it generates in a Slack channel. It says there's a new GitHub star, and it gives the example of the GitHub repo, and it says the amount of stars that that GitHub repo currently has, and it gives you the name of the person that made that star. This is that application in motion. So on the left is Slack, on the right is GitHub. I click on the star icon, and then 2 seconds later, there's my message posted up in my Slack channel. Super simple, very nice little use case of sort of getting started with serverless there. Okay, so what actually just happened? There's some business logic involved in that. Now, before joining AWS, I hadn't really thought about or used the term business logic very much in any web apps that I was building. I was just writing code. But business logic can broadly be defined as doing something to some data to produce a valuable output. And with building any kind of application in general, back to the beginning of building applications, you normally have an input, a process, and an output. And that doesn't change with Lambda. You still have an input to your Lambda function. Your Lambda function runs some kind of transform or some kind of compute on that input, and then it produces an output. So let's have a look at what the input would be for this particular example web application. So this input is provided via GitHub. It's sent on that webhook mechanism. And it's a JSON block which contains some information. This is just a subset of that information. It's much bigger than this in actual fact. But it has useful info like the name of the repository, the number of stars on that repository, the name of the user who performed the star action. And this is provided to my Lambda function as a JSON object. Then we have the Lambda function itself. Now, this is the process part of our little equation here. So Lambda is a service that runs code that you upload to it in response to events. And crucially, you only pay for the amount of time that your code is running down to the single-digit millisecond at a certain memory that you've configured for it. And that's really important. We'll come back to that point a few times, I think, in this talk. So here we have the input at the top. Hang on, let me go back one slide. Remember, this is the input, a JSON payload. That input is then provided to this function as an event object. And you can see this function is called a handler function. Now, this is written in Node.js, which is one of the managed runtimes available for Lambda. Every Lambda function needs something called a handler. It's what tells the Lambda service where to start running your business logic. So this event is passed, this input is passed to my handler as something called event. Then the next part is the process, right? Here I create a new JSON payload where the text says there is a new star event, and to that text I grab the name of the repository from that input payload, and then I use a node module called Axios to send another HTTP request onto my Slack channel. And then the output of this is the stringified result of that post to my Slack channel, along with the status code 200. So input, process, output. It's still there in my Lambda function. Nice and plain to see. OK, the missing piece, though, how did that event payload get from GitHub to my Lambda function? How did it know how to access my Lambda function? And anyone who's built any kind of web applications with Lambda will probably have already assumed that I've used Amazon API Gateway to access that Lambda function. And you would be correct. So Amazon API Gateway is a fully managed service for creating APIs at almost any scale. And you can use it to act as a kind of front door to your back-end services and your back-end business logic in your AWS account. And you can kind of lock that front door and have it authenticate in lots of different ways. But for the purposes of this demo, I'm using API Gateway to generate a URL that I provide to GitHub. The GitHub webhook sends the payload to that URL, and it invokes my Lambda function for me. OK. Why build that in serverless? Why build that using serverless technologies? I could have done that in PHP. I could have done that in Node. I could have used my own on-prem server. I could have used an EC2 instance. Why go to the trouble of building that using serverless technologies? So back in March of this year, I was creating some new getting started content for developers. And I reached out to the developer community on Twitter to ask, please share, what does serverless mean to you? What was difficult when you started learning? What were you surprised about? And this informed a whole blog series. Now, the people that responded to this are quite far along in their serverless journey. They're like relative experts in serverless. So what they say, I think, is quite interesting, and I wanted to just share a couple of those responses because some of it's not the same as what we say at AWS. So this person says, serverless is not worrying about anything other than the code and the billing. And he was surprised that Lambda is actually fast, massively parallel, and terrible with state management. Fair enough. It means I have to deal with servers less. Okay, that person's on message. I do not have to provision and maintain servers. Developing global enterprise scale apps with ease. Just put my code to work. So there were over 100 replies to this, and each one had more threads that generated more conversations. So it's a really good tweet to go back and look at to see why people are using serverless technologies. Broadly, though, they can be summarized in these three categories, right? Developers don't want to when their workload is idle. So with Lambda, you only pay for the duration that your code is running down to the single-digit millisecond, right, at the memory that you configure for it. They only want to write business logic. So what that refers to is developers offloading some of the parts of their code to other managed services that can already handle that, and then using their Lambda function just to write the pieces of their application that AWS services are not already designed to do. That's the business logic that differentiates your application from somebody else's. And the third one is, I want my application to scale on its own. Scale on its own. Now, that's a huge part of what serverless technology gives you, and a big part of Lambda, too. Now, a good way to explain how Lambda is able to scale so agilely, I think, can be exemplified with this example of the difference between vertical and horizontal scaling. Now, Lambda scales horizontally. Most traditional web architectures will scale vertically. So this is a nice analogy, I think. Imagine it's the end of the week, you're at reInvent, you've had a stimulating week, and you decide to go and let your hair down at Replay, the big sort of closing ceremony for reInvent. You choose to take a bike to get there because it's a reasonable method of transport for one person. Then, in the expo hall, you bump into some friends from this session. You're really full of ideas about building interactive Lambda applications, and you decide you want to continue your conversation and travel together to the party. So you take a cab, because a bike's not going to be big enough to fit all three of you. On the way to the taxi rank, you bump into another friend, and you decide that you're all going to go together, and now a taxi's not big enough. You need to grab a bigger transport vehicle. The idea, not just a story about making friends, each increase in load here requires the purchase of a larger transport mode to bear that load. That's an example of scaling vertically. Now, if you apply that same analogy, but you're going to scale out horizontally, then you can see exactly how it works just by this imagery, right? Each person takes their own bike because you add an additional capacity unit in line with the demand. So let's bring this back to serverless again. Another way of looking at this is in terms of capacity, and that's capacity used and capacity unused. So a traditional web application, you'll provision a machine, a server, a group of servers, maybe even a container, and that will have a certain amount of capacity to service a certain number of requests. And as your application starts serving more and more requests, you'll reach a certain threshold at which you need to clone that machine or scale that out in some way. And then your application can continue to receive more requests reliably. And then you'll reach another point where you need to scale up again. Now, the point here is that each time you scale up, you need to keep this buffer of unused capacity so that you never kind of extend into it and your application doesn't fall over. You're always paying for that unused capacity, right? Because you pay for these things by the hour, by the year, by the month. With horizontal scaling, Lambda function is spun up and run in response to each event. It gets its own execution environment, and it shuts it back down when it's finished running. And you only pay, once again, for the duration that that function is running on. And then this is the part of serverless that lots of people talk about, is I have to think about servers less, right? So when you build a web application with a traditional kind of architecture, you'll have to think about things like raising a ticket, provisioning the servers, maintaining that server. Then you have to configure your load balancing, your patching, your updating. You have to make sure it's secure. You have to make sure you have regular backups. You might have to configure some kind of network access. The idea with serverless and with Lambda is that you can get started much quicker, right? You just need to choose which runtime you're going to go ahead with. Now, of course, Lambda has all sorts of configurations that you can make, but they're optional. You can just go ahead and start building, start writing your business logic. Now, a common challenge that we see developers running into when they start with Lambda is they start cramming in more and more code into their single Lambda function. And this can lead you to some problems further down the line sometimes. So take my GitHub to Slack example. Imagine that's running nicely, and my boss comes to me and says, Ben, that webhook that you did for GitHub to Slack is running really well. We'd like to also know whenever somebody clones a repository. And I say, OK, boss, I already have my API gateway URL. I already have my Lambda function. I know it's all working nicely. I'll just point GitHub to send to my API gateway URL whenever somebody clones my repo. And then in my Lambda function, I'll write a bit of code to capture if the inbound event is a clone or if it's a star event, and then I'll run the output accordingly. Now, this will scale because Lambda is still scaling automatically in response to all of those requests. Then my boss comes back and he says, actually, we also want to capture when somebody comments on a repo. And so I add some more code. And we also want to capture whenever somebody makes a pull request. And again, I add some more code. The problem with this is the more code I add, I'm creating this kind of mini Lambda monolith where I've got this tightly coupled code base now. Now, this creates a slower release cadence because every time I add some new code, I need to check that I've not broken my function with the code that was already there. And if it does break, I have to read through all of that code once again and discover where the error is. So I'm adding complexity that I needn't have put in there in the first place. There's better ways to do this. The other problem is that with this application, between GitHub, my code, and Slack, if something's going to go wrong, well, it's most likely to be my code. And the reason is that it's my code, right? And I'm not the best developer in the world. I'm not even the best developer in my house. So these sort of faults happen all the time. I'm sure many of you here are far better developers than me, but I'm also sure that from time to time your application doesn't quite do what you expect or that you have some errors in it. So reducing the amount of code that you put into your Lambda functions helps to mitigate kind of problems. OK, so back to this example webhook application connecting GitHub to Slack. How can we improve that? One way to improve this interactive Lambda application is to start thinking asynchronously. So let's have a look at the difference broadly between synchronous and asynchronous workload. So a synchronous command works like this, where my initiating service or my client sends a request to service A. Service A might send that request downstream to service B. Service B will run, send the response back to service A. Service A might do some additional computation on that response and then send it back to the client. That's a synchronous command-driven workload. If you employ an asynchronous workload for those same services, it will work like this. Client calls out to service A. Service A sends back an acknowledgement really quickly to the client to say, OK, I'll go ahead and do that. And then in the background, it calls out to service B. Now, one important difference here is represented by this orange dotted line. This represents the amount of time your client is waiting before it hears back from service A. And the reason this is important is that this time is blocking time, right? Your application can't move on to the next procedure until it hears back. So one easy question to kind of think about when you're choosing if you should run your workload synchronously or asynchronously is, do you really need to wait for that result before your application moves on, or can you grab that result later? And if you do need to wait for it, then you probably should run that synchronously. If you can access that result later, then you should think about running it asynchronously, especially if you're using serverless technologies. Now, there's a couple of different invocation models for Lambda, and two of them are listed here. So one of them is to invoke your Lambda function synchronously. And this is basically invoking your Lambda function via an HTTP request. So that could be from API Gateway, or it could be from ALB, Application Load Balancer. And you send your HTTP request to API Gateway. That kind of proxies that payload on to the Lambda service, which runs your function. It waits for your Lambda function to finish running. Your Lambda function sends back the result to API Gateway, and API Gateway proxies that result back to you, the client, right, the requester. If you use the asynchronous invocation model from an event-based source like Amazon EventBridge, an event is put onto your serverless event bus. That's run against all the different rules or filters in your event bus. If a matching rule is found, that's then routed onto the Lambda service, and the Lambda service then picks that off a kind of internal queue that's not visible to you, but it picks that off the internal queue and runs your code against it, and significantly here, doesn't return a response back to EventBridge. EventBridge doesn't care about what happens to that event once it's left its serverless bus. So in terms of code, this is what it looks like for the asynchronous model, right? You receive a status code 200, assuming your function didn't error, and you receive the response, the body key of the JSON response object. With an asynchronous invocation, you receive a 202 success message, and you don't receive any response. So the broad thing that I want you to take away from that little sequence of slides is that if you invoke your Lambda function asynchronously, you just receive an acknowledgement that it's going to go ahead and invoke Lambda. If you invoke your Lambda function synchronously, you receive the result of that Lambda function invocation. Now, this is where it gets a little bit confusing, because just because you invoke your Lambda function synchronously, it doesn't mean you can't kick off asynchronous background processes. You can. So one example would be I could invoke my Lambda function using API Gateway, and then in my Lambda function code, I can use the SDK to schedule a step functions workflow. And that step functions workflow, it won't wait for the step functions workflow to finish. It will just send back an acknowledgement that it needs to schedule my step functions. Another example is this Slack webhook. So when I post to Slack, Slack actually sends back an acknowledgement that it's going to post to my channel. So part of my example here is part of it's asynchronous, part of it's synchronous. Okay, so back to this. How can we improve this example? Let's take away Slack and GitHub. Let's take away the services first, so we're left with the components of our application, API and compute. All web applications pretty much will have that. Then we'll take away Slack and GitHub. So this is what we're left with. One great way to improve this application and think asynchronously is to store my inbound payload before I run it against my Lambda function. Store first, process after. That really changes the way this application works. It gives me more reliability because now I'm storing that payload before my function code is able to run against it and potentially lose what that payload was. It reduces the code in my Lambda function. So imagine that I was writing from to a storage service, right? That would be extra function code, whereas if I did it this way, I can go from API Gateway directly to a storage service without any function code. This is the really cool bit about this, is that it creates a much faster response time because I'm going from API Gateway to a storage service that will send me back an acknowledgement that it's going to store my payload. And then asynchronously, that storage service will invoke my Lambda function, right? So API Gateway is not waiting for my my Lambda function response. Then I process after. One of the benefits I get from processing after, apart from just that I can do it asynchronously, is that I can use rules to route to multiple different Lambda functions that can do things all concurrently, right? So I can do more things in less time. So how do I make that work with what I already have? I'm going to add in a service called Amazon SQS, Simple Queue Service. And this is a service that you can use for creating queues in your applications. You can create first in, first out queues and last in, first out queues. So what I do is I use API Gateway, which has something called native service integrations. So this allows me to send a payload from API Gateway to over 100 different AWS services without a Lambda function in the middle. I can send directly from API Gateway, right? And another thing I can do is I can actually modify that payload to some degree before it gets sent on to SQS. And I can modify that payload using VTL, Velocity Templating Language, which again is taking some of that function code out of my Lambda function and putting it into the configuration of other services. Then I invoke my Lambda function from SQS. This is called event source mapping. So I can do this with DynamoDB streams and Kinesis as well. It's a different Lambda invocation type. This way, I can configure a batch number, so a number of payloads before it invokes my Lambda function. So I can say, wait until I have 10 actions from GitHub, and then send all of them to Lambda at the same time and do them all together. And it's all asynchronous. It reduces. So launched about 4 days ago was this brand new feature for event source mapping. You can create filters for your event source mapping, right? So what this means is that you can create a kind of JSON matching filter. It's the same as when you create an event bridge filter, the same format. And you can tell it to only invoke your Lambda function if it meets the pattern that you set in your filter. So for example, I could say I only want to invoke my Lambda function if it's a star event from GitHub, if that's present in my JSON payload. If it's not present, it will still take that message off the queue as if it's been successful, but it won't invoke my Lambda function. And that's good because that means I don't have to put that logic in my Lambda function, right? If I put that logic in my Lambda function, then my function would have to run in order to check if it needed to do anything. So I'm reducing the amount of times I need to invoke Lambda. I'm reducing code from my Lambda function. This is an example of what that pattern looks like when you create it with AWS SAM. Excuse me. OK, so final slide for this example. How can we improve it? We go from API gateway, we store first, we process after. We turn it into an asynchronous workload, right? So we store it in SQS. SQS sends back an acknowledgement to API gateway that it's going to store that. Then we can branch out using filtering to our Lambda functions. So I built this using the synchronous version and the asynchronous version. So the synchronous is on the left and the asynchronous is on the right. The top row shows the average API latency, and the bottom row shows the average Lambda function duration. Now, notice the average function duration is about the same, because our Lambda function is doing exactly the same thing, right? We didn't change our Lambda function at all. What's really interesting, though, is the API latency. So with the synchronous way of doing this, my API gateway is waiting to pass on the payload to Lambda. Lambda then does the transform. It uses Axios to post out to Slack. It waits for that acknowledgement back from Slack, and then it passes it back to API gateway and back to the user, and that takes, on average, 252 milliseconds. The asynchronous version, API gateway tells SQS to put something on a queue, and it gets an acknowledgement back, and that takes, on average, 39 milliseconds. So that's a great improvement in the latency for the initializing service. I didn't have to use SQS. I could have used any number of storage-first options. I could have used Kinesis. I could have used EventBridge. Could have used DynamoDB. I could even have gone from API Gateway directly to S3. Problem with that example, so we improved the API latency, but it doesn't really matter in that example because GitHub is what's making that request, and I don't really care if it takes 42 milliseconds or 250 milliseconds because GitHub's handling that. So let's have a look at a more sort of web user-based example and see how we can improve that. So this is more like a web application than a sort of payload example. This is a web app that translates some text into different languages and produces an MP3 file of that translation as well. This is the input that I provide to that application. So I'll read it out. It has a data value that says, hello, welcome to my translation demo. And then it has a key called culture with an array of languages, French, Turkish, German, French Canadian. I'll just take this off because I think it's probably banging on my mic. So here's that application. My user submits that payload to API Gateway. It goes from, this is the synchronous version of that application, right? Synchronous version. It goes from API Gateway to my Lambda function. My Lambda function then posts or uses the SDK to send each one of those translations that it needs to make onto a service called Amazon Translate. Amazon Translate then returns the translated version of that text to my Lambda function. My Lambda function then collates all of them and passes them on to a service called Amazon Polly, again using the SDK. Amazon Polly generates an MP3 file for all of the translated text and passes that back to Lambda. Lambda then saves all of them in an S3 bucket. After that, it will save some metadata about that whole process in an Amazon DynamoDB table. And this is the output, right? So the top one is DynamoDB, and it has the text translations and the original input. The bottom one here is S3, and that has the actual binary MP3 file. It's a real application. OK, if I were to build that asynchronously, how would that look? And why would I do it, right? My Lambda function in the synchronous example is procedurally calling out to multiple AWS services, waiting for the response, and then calling out to the next. Now, when I invoke Lambda using API Gateway, there's a timeout limit of 29 seconds, OK? So imagine if I'm uploading a big body of text. I only have 29 seconds for my Lambda function to do all of that code, and each time it's waiting to receive a response back from all of those services. So if we implement this asynchronously, it will look like this. We start with API Gateway, and then we store first, process after. So we go from API Gateway directly into a DynamoDB table. Then from DynamoDB, we use a DynamoDB stream to parse that data to a stream reader, a Lambda function. That Lambda function then puts events on our Amazon Event Bridge. And here's where the kind of magic starts to happen. Amazon Event Bridge matches that against all the different rules that it has assigned. There'll be a rule to send that message to a translate Lambda function, which will call out to Amazon Translate. Amazon Translate will call back, and it will store that result in a DynamoDB table. At the same time as the translation's happening, there'll be another rule matching to an audio Lambda function, which will interact with Amazon Polly to create the MP3 file. Amazon Polly will then write that to an audio, a bucket on S3. The write to the bucket on S3 will trigger another Lambda function called the finalize function, which will save the location of that MP3 file back to my DynamoDB table. So all of this is kind of firing asynchronously, a lot of it concurrently at the same time. So the behavior of this application in the synchronous version and the asynchronous version is pretty different. So here's how it looks, right? In terms of the blocking time, in the synchronous version, my user, my caller, is waiting until the end of the process for a response. So it has to wait for the whole application to finish translating everything before it gets a response back saying, done. In the asynchronous version, my user gets a response back straight away saying, OK, we're going to translate that for you. You can go ahead and browse the app. In terms of cost, so in the synchronous version, my Lambda function, as I mentioned, is waiting for each function for each service to do its thing and call back. And you're paying for that wait time, right? Your Lambda function is sitting there. It can't shut down because it needs to wait for the response. So you're paying for that idle wait time. In the asynchronous version, you're minimizing that wait time because you don't have one Lambda function that's just sat there waiting to hear back. In terms of latency, with the synchronous version, any latency in the application at any point affects the overall latency of the whole application, whereas with your asynchronous version, it's just contained to that particular part of the workload. With the synchronous, again, in terms of durability, any failure, the whole workload will just break, right? With the asynchronous, if there's a failure, it will only fail on that little part, but there becomes a challenge. You have to capture those failures, and we'll look at that in a second. In terms of the implementation, I think synchronous is an easier thing to implement because it's the way our brains think, right, procedurally, whereas asynchronous is a bit more complex. But it's worth running your Lambda function, your workloads asynchronously when you're building with Lambda. A few reasons. Your application becomes much easier to extend. If I needed that application to do something else, I could just generate a new event on EventBridge and route that off to another Lambda function. It's much faster response time for the end user. There's less code overall. And the reliability can be increased, and I'll show you how that's done. So here's my application, the asynchronous version. I've got 4 Lambda functions in this application. And each Lambda function has the business logic, has the code, and it has a bunch of error handling to handle things that go wrong, try-catch statements. Maybe it's routing off to other services if things break. Now, it would be better if I could handle all of those errors in one error handling Lambda function and then take all that error handling logic out of all the other functions, right? Much cleaner, much easier. I can do that using something called Lambda destinations. Now, this was a feature of Lambda that was launched, I think, 2 reInvents ago. And what it allows you to do is if your Lambda function fails, you can route those failures to any one of these 4 services, and you can handle them later. Interestingly, if your Lambda function succeeds, you can route the response to the same 4 services. Now, we've seen some interesting kind of chaining of Lambda functions from customers. I would advise not chaining too many Lambda functions together, because then you start to create a kind of workflow, and there's other services that can manage that better, for like step functions, for example. But on failure events, I think it's a great way of capturing failures in any one of these services. So back to my asynchronous application. I capture all of the failures in a single error handling Lambda function using Lambda destinations. Then from that error handling Lambda function, I write those failures back to my DynamoDB, my single source of truth. Remember, one of the Twitter users said Lambda difficult for state management. Well, in this example, I'm using DynamoDB to manage the state of my whole application, right? That's my single source of truth as my payload passes through the various stages. Then I have another Lambda function which can be on a scheduler to scan through my DynamoDB table and kind of correct some of those errors every day, every hour, for example. Okay. So what I've done there in using the asynchronous version is I've taken a lot of that logic out of my one Lambda function, and I've moved it into the various managed services. So I've reduced code in each of those Lambda functions. I'm using each service for the thing that they were required to do, and offloading that to my services, and I can concentrate on just writing the business logic in my Lambda function. Another boost that gives me in using managed services is a security boost. So traditional applications are based more on this kind of castle and moat security model, where you build one big perimeter around your application. And if I'd used the synchronous version of my translation app, it would be similar to this, right? Because I have one Lambda function doing everything. One big perimeter around the whole application. With serverless and with AWS, you're able to employ this zero trust model where you build these micro perimeters around each service or each part of your application. And that enforces much stricter verification of every person or every service that's interacting with each other. So what that means is if there's a breach in your castle moat security framework, that intrusion now has access to your entire application. Whereas with the zero trust, it only has access to that one micro perimeter that it breached. The way you employ that in AWS is by using IAM, Identity and Access Management. And with Lambda specifically, you would use resource policies and execution roles. So a resource policy defines what services are allowed to invoke your Lambda function, okay? And an execution role defines what your Lambda function is then able to interact with. And by default, both of these are set to nothing, to 0. So when you first build your Lambda function, it can't do anything apart from write to CloudWatch logs. That's really annoying, actually, when you first start using Lambda. At least it was for me, because I could never figure out why my function code was returning errors. But it was because I hadn't set security permissions that it needed, right? So here's an example of me applying an action called invoke function to an API gateway resource policy, which would allow a certain API gateway resource to invoke my Lambda function. And then my execution role here, it lets my Lambda function put items onto a specific DynamoDB table. That's all this function is able to do, right? This function would be designed for putting things onto DynamoDB, and it's restricted only to doing that. It lives a very focused life. Okay, there exists this application called Serverless Espresso. And this is something that myself and the rest of the developer advocate team built especially for reInvent. It's a live coffee bar in the expo hall in the Venetian, where you can go up and order a coffee, and it'll be made by a real barista. And the whole application is built on serverless technologies, and it's open on these hours. The reason I want to show you this because it employs a lot of the things I've spoken about today, using the managed services, using asynchronous workloads where possible, and another thing that I want to tell you about. So this is broadly how it works. It has 3 front-end applications. One is a web app that you go to on your phone to look at the menu and make your order. Another is an application for the barista, the people making the coffee, where they can see orders coming in. And the third is a kind of display app above the booth to see where your order is progressing in the queue. We use API Gateway to allow you to communicate with the back-end resources, to allow all those front-end applications to invoke Lambda functions and other services. Then we use Amazon EventBridge to generate events for all the back-end processes to kind of communicate asynchronously. Each time you order a coffee, your coffee journey from the initial order to the final completion is kind of managed or orchestrated by an AWS Step Functions workflow. This is the next bit I want to talk about. We use IoT topics to update the front end about where your drink is in the process, right? So this is the next challenge, I think, with using asynchronous workloads in web apps, is that you need a way of handling response values and state for those asynchronous requests. Remember this animation. There's no path to find out when this particular task is finished or what point it's at, right? There's nothing obvious to know how to find out the update of this particular task. There's a couple of ways of dealing with this. One way is by using something called polling. Now, polling reminds me always of going on a long car journey with my daughter where I'm driving and she's, "Are we there yet, Dad? No. Are we there yet, Dad? No." And it goes on for the duration of the journey, and it's very annoying, but it works really well because she gets constant status updates about where we are during the journey. She's polling me for updates. And this is one way you can get information about your asynchronous workload, right? Your initial request that triggers your Lambda function will return back an identification. So Amazon API Gateway returns back a GUID, which you can save against that request and use that for subsequent requests to see how that's progressing in the system. Then you can create a second API endpoint, and you can use that in your front end to poll the status of that request at regular intervals, right? So you can poll DynamoDB to check the update on your request. There's a couple of problems with this. So the first is that if you poll too often, you're going to be often getting back empty results, like this example here. Is it ready yet? No. Is it ready yet? No. Now, you can adjust that by polling at less frequent, but then you have the reverse problem, is that there might be quite a big time delay between when your workload is finished and when you receive the information that it's finished. It's relatively simple to implement this, though, and it can be quite effective. Another way of handling asynchronous workloads is by using WebSockets. So, to use my analogy of driving with my daughter, this would be me saying to her, I'll let you know when we get there, and then every 10 minutes I'll tell her, 10 minutes left, 5 minutes left, 4 minutes left, we're there. That doesn't seem to work with her, but it's worth a try. WebSockets set up this kind of bi-directional connection between the front end, your application, and your back-end services, right? And you can use that connection to send messages back to your front-end service without having to poll the back-end. Now, before joining AWS, I'll be honest, I was quite put off by WebSockets. I didn't really understand how they worked. I always just resort to using REST APIs. I still don't really understand a lot about how WebSockets work, but the good news is you don't actually need to get right into it if you use IoT Core, which is what I'm going to show you next, because that's all managed for you. And that's what serverless is, right? Offloading some of that heavy lifting to manage services. Now, the benefit you get from using a WebSocket connection is much closer to real time, because your application backend is calling directly in to your front-end application as soon as it also reduces the number of these empty messages that you're sort of polling for. but it can be more difficult to implement. With modern web applications, people don't just expect them to be fast. They expect frequent updates about the thing that they're doing. So for example, when you use a food ordering app, you expect to know how long until your food is there, and you expect the screen to update, maybe with a map to show you where that person is as they're arriving. Or another example, maybe you're returning something to a furniture store and you have to take it. You expect to know how long you're going to be waiting for, how you're progressing in the queue. You don't expect it to be quick, but you do expect feedback about the request that you've started. A more simple version might just be a upload completion percentage. And we use this in that serverless espresso example. There's various states that your coffee goes through, from you submitting the order to the order being ready for you. And we update the app with each one of those states so that you know that your order's progressing, even though it will take 5 or 10 minutes for your coffee, maybe. Here's how we do it. So we use IoT Core for real-time messaging. So IoT Core is another service on AWS. We use the AWS SDK to set up this WebSocket connection via IoT Core. It's a pub-sub connection that allows your front end to then listen for updates from an IoT Core topic. Okay, so the first thing that you do when the user logs in, when you log into Serverless Espresso, we grab your user ID and we use that to subscribe you to your own unique topic on IoT Core. Then, whenever there's a relevant message update about your order, your coffee, we publish that message to your specific IoT topic that your front end is subscribed to, and you see that message appear in real time. Now, a topic is just a way of grouping messages together based on a string, based on a name. So, like I said, with Serverless Espresso, we use your user ID. This is a really powerful pattern because it allows you to fan out to thousands of front-end devices just by subscribing to a unique user topic. You can also subscribe to a global topic. So let's say when your user logs in, you want them to subscribe to their own unique topic and a global topic that might say the shop is closed or some big event that every user needs to hear about. This is a great way of running Lambda with asynchronous invocations, which is reducing code, saving your Lambda runtime, and still receiving updates about the status of those requests. Here's how you implement it in code. So this is using the IoT data class in the AWS SDK, which uses MQTT protocol. So these three different events are capturing different things, right? The first one is when the initial connection is made. The middle one is whenever there's an error, a message being reported back. The third one's the important one. So this is capturing whenever there's an inbound message from my IoT topic that my front end needs to tell the user about. And what I would do is I would put in this function, I would put some kind of switch or else if statement to check what that event is, and my application can react to that accordingly without having to poll any back-end services. Realistically, in the real world, your web applications, your interactive Lambda applications will probably need to use a mixture of synchronous and asynchronous workloads. And that's true of this Serverless Espresso demo that we made as well, right? So we use a synchronous workload when you first log into the app, which uses API Gateway to grab all the information from our DynamoDB table about the current state of the shop. This includes things like open and close times to check if you're within those bounds, if the shop's open or closed. It includes things like the menu items that are available to see what you're allowed to select. At the same time as that, once you're logged in, at the same time we subscribe you to a global IoT topic, which every user will receive messages for, and to a unique IoT topic, which your front end will receive messages for. And then our application is doing all sorts of things asynchronously with state machines and with EventBridge. And whenever there's a relevant message that's important for your front end to hear about, it will use the Lambda publisher service to publish a message onto that IoT topic, and that gets sent back to your front-end device. And there you go. You have live, kind of near real-time status updates about your asynchronous workloads. So just to recap, I've mentioned a lot about synchronous and asynchronous here. The idea with asynchronous is that it cuts out the need to kind of reduce. Interactive workloads have often been talked about in terms of preventing cold starts, right? Making your function warm, using provision concurrency, things like that, making your function work as quickly as possible. But I think of it a bit differently. I think serverless is really designed for using asynchronous invocations, because much more often than you think, you don't actually need that result right away. You can use things like WebSockets and polling to grab that result later on in the application. And if you invoke your Lambda functions asynchronously, you get all the benefits that I've mentioned in this presentation. You get extra reliability, you get extra state management, you get a different way of being able to retry your function with Lambda destinations. So use asynchronous workloads wherever possible. The next thing is to try and reduce code in your Lambda functions. This will sort of decrease the cognitive load that you need to understand what your function is doing. And it will allow you to write more specific code. And the best way to do that is by using the services. So lean into the services, configure the AWS services to do what you need them to do, rather than writing more custom code, more routing into your Lambda functions, more authorization into your Lambda functions. Use the services as and when you need. And then the third important thing here is to put storage first. Back to that person that mentioned on Twitter that Lambda is not great for state management. Okay, that's one of the reasons it's able to scale so effectively, but there are other services which are great for sort of quick data storage and retrieval, like DynamoDB, for example. So use those services to store state about your application as much as possible. And that's really it. Thank you so much for listening.